Welcome to Stats and Mechanics Chapter 7. So it's the Stats and Mechanics book, Chapter 7, which is mechanics again, it's applications of forces. This chapter very heavily relies on a sound grasp of Chapter 4, which was moments, and Chapter 5, which was forces and friction. So these ideas are going to be taken further, developed, and then put into practice with some more contextual problems where we mix these ideas together to come up with solving questions relating to all of those concepts we've covered thus far. Based on what I've said, that we need to be comfortable with moments, forces and friction, that's formed the basis of a couple of warm-up questions. So warm-up question 1 is going to look at forces and friction, in particular limiting friction. So this tests your Chapter 5 recall and grasp of that. Warm-up question 2 looks at Chapter 4 again. This is essentially a moments question. So be thinking limiting friction for warm-up 1, be thinking of moments for question 2. That's all the hints I'm going to give you. Pause the video here and try them on your own. Press play to see what the solutions to these warm-up questions are. Alright then, so let's have a look together at warm-up question 1. So we've got here a particle of mass 2 kilograms. It's resting on a rough plane inclined at 45 degrees to the horizontal. So already this is screaming out for us to do a force diagram. So let's sketch in as we go. So we've got here, that's the horizontal. It's a 45-degree angle. So I'm going to label this in like so. It's a particle, so we can just model this as just a circle. If that's 2 kilograms, it's going to have a weight of 2g acting downwards, quite obviously. We're told that it's inclined at 45 degrees, so we know this angle here must be 45 degrees. That's the inclination. And we're also told here that a force of 20 newtons acts parallel and up the plane. So this particle is being pulled upwards in this direction by a force of 20 newtons. Okay, as well as that, there'll also be a normal reaction force, which will be perpendicular to the plane. I'm going to label that N, which stands for normal reaction. And because this particle might well be going up or down the plane, it might well be worth us resolving in directions going parallel and perpendicular to the plane. The way we do that is we base this off a weight. We can resolve the weight in this direction, and it's based off this angle. This was covered in Chapter 5, and here's a recap of how we can work out the components of the weight relative to the size of the weight and this angle. So this should hopefully remind you in some way. So essentially, the component of the weight acting perpendicular to the slope is going to be the weight multiplied by cosine of this angle. And this angle here will be the same as this one here. And as well as that, the component parallel to the slope, going up and down the slope, is the magnitude of the hypotenuse, the weight again, but this time sine of this angle. So because that's 45, this will always be the same. That'll be a right angle. And then we can just use simple right angled trig to work out the red and the blue in relation to the 2g force. So that's 2g cosine 45. This one here, 2g sine of 45. Now we should know, because this is a rough plane, friction will always act to resist motion. So which is the resultant force acting in currently, imagining it was a smooth slope? So let's work out which is bigger, 20 or 20g sine 45. Sorry, 20 or 2g sine 45. Well, 2g means 2 multiplied by 9.8. And multiply by sine 45. Now that's about 13.86. Okay, so that's 13.86 going down the slope. So this is less than the 20 Newton force. So if the slope was smooth, the particle would be flying up the slope, would be pulled up because of this force. But because it's rough, the friction must be acting down the slope, resisting this tendency for the particle to be pulled up the slope. So the friction going downwards is acting that way. And we're also told here that this is on the point of moving. If the particle is on the point of moving, what that means is the friction will be at its maximum value. Friction will equal F max, which, as we hopefully can remember, is mu multiplied by n. So I'm labelling this on here, mu n. So we've labelled down all we need, really, and that's just a case of solving it. So it's on the point of moving, so it's still just about in equilibrium, this particle. It's in a limiting equilibrium. So let's think about forces acting perpendicular to the slope. So forces going perpendicular to the slope. Because it's in equilibrium, the forces going up will equal the forces, or components of forces, acting down. So in other words, the forces acting up and away perpendicularly, that's just n. And acting downwards, that's just for 2g cos 45. It's just this red component of the weight. So n is 2g cos 45, which we can evaluate using the calculator. So 2g cos 45, 2 times 9.8 times cosine 45. That gives us, again, about 13.86. So actually, of course, you can see it's 859. So it's a bit more. So I'm not going to round it yet because this isn't our final answer. So because n is 13.8ish, we can say that mu n, that equals about 13.859 mu. Mu times n equals n times mu equals 13 point whatever times mu. We can now resolve going parallel to the slope. Because it's still in equilibrium, the forces acting down will be equal to the components or the forces acting upwards. Acting down the slope, we've got the limiting friction. So friction F max is going to be 13.859 mu, and we've also got acting downwards this 2g sine 45 force. They're the only forces acting down the slope. Acting up, it's just this 20 newtons pulling force. So these two acting together must equal 20. So 13.859 and so on, lots of mu. Taking away 2g sine 45 from both sides, that must equal 20 minus 2g sine 45. Therefore, mu will be 20 minus 2g sine 45, all divided by this 13.859, etc. So let's see what that gives us. So this is stored on our calculator, so let's leave it like that. So 20 minus 2 multiplied by 9.8 multiplied by sine 45, all divided by that previous answer, which we're going to leave stored. Press equals. Horrible surdy thing. Press SROD to get it into a more understandable decimal. We get about 0.443. So that's the coefficient of friction. A fairly challenging initial warm-up question, but there you go. Sometimes you might get thrown in the deep end, as you may well do in the exam. Hopefully you won't be, but you never know. Be prepared for anything. Let's have a look at question 2. Question 2, like I said before, this is a question about moments, essentially. So again, we need to sketch this out. So we've got here a uniform rod, AB. It's got a length of 2 meters. It's a mass of 5 kilograms, and it's resting in equilibrium angled at 60 degrees to a horizontal surface. So I'm going to draw it like this, nice, big and clear. I'm going to also just sketch in the surface, which is horizontal like so. So we're told its length 2 meters, so we can add this information in. So that's 2 meters. And this angle here is 60 degrees. If it's uniform, we can assume that the weight is evenly distributed, so the centre of mass can be taken to be acting from the middle of this rod, like so. And so, if full length 2 meters, then the centre of mass we can take to be acting at the halfway point, which is just 1 meter up from where it's being pivoted. So it says being pivoted at A, so I'm going to call this point here A, that's where it's hinged. The other end is going to be at B. And we need to add in the weight as well. So its mass is 5 kilograms. That's the same as saying that its weight is acting down and is equal to 5g. Now, at B, it says that there's a force x newton acting perpendicular to the rod, so that means at right angles it's acting at B. So that's must be holding it in place because it's in equilibrium. So this force here at B must be holding it up, otherwise this would have a tendency to just fall down to the floor like so. So because it's not doing that, what we must have is the force at B acting upwards like so. And that's called x, and that's at right angles, because we're told it's perpendicular. So we need to find the value of x. So we need to find a place to take moments about. So there will be a force acting at A. So if we take moments at A, we don't need to worry about any force acting at A. So take moments about point A. The clockwise moments will equal the sum of the anti-clockwise moments. Acting clockwise is going to be the turning force, the moment, due to this weight. So remember, the moment is force multiplied by the perpendicular distance of the line of action of the force from the pivot point. So for this weight of 5g, I need to find out this distance here from A to the line of action of that force, which makes a right angle with the line of action like so. I need to find the length of that green line, essentially. So for the 5g force, the moment of this one will be 5g multiplied by the distance of that 5g force from A, which is this green line. Now this essentially is trig. The hypotenuse is 1 meter, from A to the midpoint is 1 meter. The angle's 60. I want to find this adjacent side, this green side here. So that's going to be 1 multiplied by cos 60, which is of course just cos 60. I'll leave it as 1 cos 60 in case you want to check that out using SOHCAHTOA. This would be 1 sin 60, that's 1 cos 60, and that's just 1. So 5g multiplied by 1 cos 60, so that's going to equal the moment going anti-clockwise. So relative to A, x is going around anti-clockwise, and so this is the only anti-clockwise moment. It's due to this x force. So that's going to be the size of the force, which is x, multiplied by the perpendicular distance of the line of action of the force from the pivot. We already know x is perpendicular to this line, so it's just x multiplied by 2 meters. In other words, 2 times x. So therefore, x is just 5g cos 60 divided by 2. So if we just try that now, 5 times 9.8 multiplied by cosine of 60, and all of this divided by 2, get 49 over 4, which is 12.25, which if we want to, we can round that to 12.3 newtons. It wouldn't hurt too much to leave it as 12.25, I suppose, but give it to the magical 3 significant figures. You won't ever go too far wrong, unless a question says otherwise, of course. Let's take these ideas and develop them even further. So, today, looking in particular at static particles. A particle or a rigid body is in static equilibrium if it is at rest and the resultant forces acting on the particle are zero. To solve problems in statics, you must do the 4 following things. So first of all, draw a diagram showing clearly the forces acting on the particle. The second thing we need to do is resolve the forces into horizontal and vertical components, or, if a particle is on an inclined plane, into components parallel and perpendicular to the plane in question. The third thing, we set the sum of the components in each direction equal to 0. Whoops, that is annoying. Didn't see anything, so don't you dare say. Whoops. And finally, bullet point 4, solve the resulting equations to find the unknown forces. So let's have a look at these in context. As long as you follow that recipe of these 4 things ticked off and done carefully, with enough practice you won't go too far wrong. So let's have a look at some worked examples. Let's now have a look straight at some static particles in equilibrium. So worked example 1, we've got 3 different forces, as you can see, acting on this particle. So we need to resolve horizontally and vertically, we're told, find the magnitudes of the forces P and Q. So what we need to recall from previous sessions is how to resolve vertically and horizontally. So if I just were to get these arrows in blue to denote horizontal components and red to denote vertical components of force P and the force 4, then we need to recall that the component which is opposite to the known angle is always going to be the hypotenuse sine of the angle. So in this case, for P, the vertical component is P sine 30, whereas for the 4 Newton force, the vertical component is going to be 4 sine 45. And the horizontal components, pardon me, will be the hypotenuse, or the magnitude in this case P, multiplied by cosine of the known angle. So that's going to be P cos 30 resolving for P Newton force, and over here for the 4 Newton force resolved is going to be P cosine 45. We can now choose to resolve these forces either vertically or horizontally. So because the particles in equilibrium, the sum of all the forces in any one direction will be equal to 0. And so if we were to just take the forces going horizontally, then in shorthand, the sum of the forces in this horizontal direction will be equal to 0. So, in other words, the components acting to the left will be equal and opposite to the components acting to the right. The only component here acting to the left is the 4 cos 45 degree, the horizontal component of the 4 Newton force. So going to the left, we have 4 cosine 45, and that must be equal and opposite to the sum of the forces acting to the right, which is just P cosine 30. We can therefore get P on its own. We can isolate P by dividing through by cosine 30. So P is 4 cosine 45 divided by the cosine of 30. So this is where the calculator comes in handy. So 4 cosine 45 divided by cosine of 30, press equals. We have 4 root 6 over 3 in exact form. Given to 3 significant figures, we've got 3.27. So P is 3.27 newtons to 3 significant figures. Next, we can resolve vertically. So again, the sum of the forces acting in the vertical directions will be equal to 0. Put plainly, the sum of the components acting up will be equal and opposite to the sum of the forces or components of forces acting downwards. So acting up, we've got 4 sine 45. We've also got P sine 30. So that'll be acting in the opposite direction to Q. Pardon me again, slight cold. So these two added together will be equal and opposite to Q. So they'll equal in magnitude Q. So therefore we can just work out what Q is. So therefore Q is going to be 4 sine 45. Now we can keep what P is, because we can keep P in standard form. So in standard form, P is 4 root 6 over 3. Sine 30. Then we can round after the fact. So if we calculate that for what Q is, so P is just this thing here. So let's work this out now. So 4 sine 45 plus the previous answer, we can use ANS sine 30, because ANS will be this stored value of 4 root 6 over 3. We get this horrible looking surd expression, so press SROD. We can see here that Q must be, to 3 significant figures, 4.46 newtons. So that's worked example 1 done. Let's have a look at another worked example. You guessed it, it's called worked example number 2. So, worked example 2. Looks a harder problem. I suppose it is. There's a few ways of tackling this one. I'll just mention what these ways are when we get to that point. So we've got a diagram here. A particle's in equilibrium. So again, forces in any direction are going to be balanced. It's on an inclined plane under the forces shown. Find the magnitude of force P and the size of this angle alpha. So one thing we've not done yet is had these forces resolved in directions going perpendicular and parallel to this inclined plane, which would be my suggestion. So, resolving parallel and perpendicular to the plane, we can resolve this force P. So force P will have a component like so, going parallel, and also will have a component going perpendicular to the plane. And so the opposite component is always going to be the magnitude or hypotenuse, in this case P, sine of the angle we know, so P sine alpha, whereas the adjacent component, in this case the component going parallel to the slope, will be P cosine alpha. In the same way, we can resolve the components of the weight, this 5 Newton force. Well, if it's not the weight, the downwards force, no matter what it might be, we can resolve this going perpendicular and parallel to the plane as well. So if you've forgotten how to do this, I'll remind you from chapter 5 of a technique I explained a couple of chapters ago, which is this. So if we know this angle theta, then we can do a force triangle of components over here, whereby the component going perpendicular will be the downwards force multiplied by the cosine of the angle, and the component going parallel to the plane, this one I'm doing here, where this angle here is a right angle, this will be sine of the known angle, which of course is 30. So I'm going to label this angle here 30, so it's clear where it's come from. I'm going to make a point of highlighting I know it's 30 because this one's 30. So this component here will be 5 cosine 30, whereas this parallel component will be 5 sine 30. Oops, that's the wrong colour. There we go. So we can now resolve in whichever direction we choose. So what I'm going to choose to do first of all is I'm going to resolve perpendicular to the slope. So thinking perpendicular to the slope, so the total of the forces going perpendicular, sort of up, will be equal to the forces, or components of forces going down. So in other words, up will equal down. So therefore, going up, we're going to have up and away from the slope, we've got P sine alpha plus this 2 Newton force. And going downwards, perpendicularly down, we've got 5 cos 30. So we can get P sine alpha. So P sine alpha equals 5 cosine 30 minus 2. Now forces going up and down the slope, forces going down will be equal and opposite to the forces going up the slope, because again it's in equilibrium. So the forces acting down, well, acting downwards, we've got this big 8 Newton force. Excuse me. Also have this 5 sine 30 force plus 5 sine 30. And they'll be equal and opposite to the forces acting upwards. So in this case, that's going to be equal to P cosine 30. Sorry, P cosine alpha, I mean to say. So in other words, we've got P cosine alpha. So I'll write this underneath this one. That equals 8 plus 5 sine 30. Now we now have a few ways to proceed. There's now a few things we can do. Now, my suggestion here is if I label this equation 1 and that bottom one equation 2, I can then do equation 1 divided by equation 2. And if I do that, on this side, I'll have P sine alpha divided by P cosine alpha. The P's will cancel, and then I'll have sine alpha divided by cosine alpha, which will be tan alpha. So I will have eliminated P, and we'll end up with tan alpha. So tan alpha will be the top equation, 5 cosine 30 minus 2. All of that divided by 8 plus 5 sine 30, like so. So we can evaluate this on the calculator to get the value of tan alpha. So tan alpha, we just can type in 5 cos 30, 5 cosine 30 minus 2, all of that divided by 8 plus 5 sine 30. So we get this third, and to be honest, we can leave it like this. So we get minus 4. I forgot what it was already. Minus 4 plus 5 root 3. All divided by 21. So therefore alpha will be tan minus 1 of that. So if I just do shift tan minus 1 of my answer, I've got 12.5 degrees to 1 decimal place. Now I know that alpha is about 12.5. I can then sub that back into one of these initial equations. So if I now sub that back into, say, let's just go for equation 1. If I substitute that into 1 and rearrange, I'll get that P is 5 cos 30 minus 2, and if I divide everything by sine alpha, so sine of 12.5, now don't round this at this case, so don't round this because this isn't the final answer yet for the part where we're working out the magnitude. So use that exact value on the calculator, so sine of 12.51 ... just to make it clear that we're going to use the exact value of this angle. So we have 5 cosine 30 minus 2 divided by sine of that answer stored in my calculator, and that gives me three significant figures, 10.8. So P, the magnitude of P, is 10.8 newtons. I want to now have a look at an exam paper question from very many years ago, before many of you were born actually. This was 2002. Let's see if we can tackle this one. Now this also uses the idea of limiting friction, so it needs a mastery and an understanding of everything we covered in chapter 5 of the second year mechanics course. So here we've got a ring of mass 0.3 kilograms. It's threaded on a fixed, rough horizontal curtain pole. A light, inextensible string is attached to the ring. The string and the pole lie in the same vertical plane, so it's both in the same 2D plane these forces are acting. The ring's pulled downwards by the string, which makes an angle of alpha to the horizontal, where tan alpha is 3/4 as shown. The tension of the string is 2.5 newtons. Given that in this position the ring is in limiting equilibrium, find the coefficient of friction between the ring and the pole. So first of all, what I want to do is be a bit more elegant with this use of tan alpha. Okay, so let's just dwell on this for a moment, tan alpha. So one way we could work out what alpha is would be to do tan minus 1 of 3/4, and I'll show you another way in a moment. I'm going to put this in a little thought bubble over here, so it's not the main way of what I'm going to show you as a better way. So alpha is tan minus 1 of 3/4. So if we do that now, so shift tan minus 1, 3/4, we get 36.869 and so on. So not a very easy figure to work with. So 869, I said yes. So therefore, sine alpha means sine of that 36.8 blah blah blah. So if we do sine of the answer stored, so press A and S, so don't round it at all, I get 3/5. So I'm going to call that a decimal, so sine alpha is 0.6, and also cos alpha, because of that 36.8, so on and so forth, feel free to try this yourself, you would get 0.8. I want to explain why that is. So if I just take this triangle here with alpha in it, so we're told what tan alpha is. And we need to remember from GCSE what the tangent function tells us. The tangent function tells us the ratio between the opposite side and the adjacent. So opposite to alpha is this one. So the ratio of this side to this side is 3 to 4. And if we do that, tan alpha is opposite divided by adjacent, 3 over 4, so it works. But from this construction, we can then work out what the corresponding hypotenuse would be by using Pythagoras. This side, squared, would be 3 squared plus 4 squared, which is 25. This side would therefore be the square root of 25, which is 5. Then we can use the idea of what sine is. Sine is the opposite divided by hypotenuse, which is 3 divided by 5, in other words 0.6. Similarly, for cosine, cosine's adjacent divided by hypotenuse, 4 divided by 5, which again is 0.8. So this is a more elegant way of working out, and more than that, understanding where this value of alpha comes from and why it's written in this neat form which it is. We can then go forward and tackle this question. Now, it says the ring is in limiting equilibrium, and that means friction is at the maximum. Friction is F max, and like I mentioned, you need to know about chapter 5. So F max is going to be mu n, where mu is the coefficient of friction. So friction will always act to resist motion. So in this case here, friction will be acting opposite in direction to this force here, but it'll be acting along this pole. So the pole, which is rough, will be providing a frictional force going the other way. Otherwise, if it didn't, the ring would slide along in this direction. And so F max is acting this way, and that's going to be mu n. There's also going to be a weight, because this ring obviously has a mass. So we're told here that the mass of this is 0.3. So if its mass is 0.3, its weight is going to be 0.3 g. And the normal reaction will be perpendicular to the direction of this pole. So the normal reaction force in this case will be going upwards as we look at this diagram. So N is angled upwards like so. This force here, that the tension in this string, can be again resolved going along the curtain pole and perpendicular to it. So if we resolve this here, let's pick a different colour. Let's pick, I don't know, maybe a purple. Do it in a dotted line. It's got a component going along and a component going down like so. So, like you should know by now, the component which is opposite to the angle in question is the magnitude multiplied by sine of the angle, so 2.5 sine alpha. And this component here is going to be 2.5 multiplied by cosine alpha. So now that we have that, we can resolve either perpendicular or parallel to this curtain pole, and the choice, to be honest, is ours. Now, what I would personally suggest is to fill in the value of these two components, because we've worked out what cos alpha and sine alpha are. So because we know that sine alpha is 0.6, we can just do 2.5 multiplied by 0.6. So again, if this is in any doubt, just use your calculator, I suppose. So 2.5 multiplied by 0.6, try it if you want to. You'll get 1.5. So 1.5 newtons going down, and going along, 2.5 cos alpha means 2.5 multiplied by 0.8, and that's going to give us 2 newtons if you're to try that on a calculator. So like I've said, we can resolve in any direction first, but actually it turns out if we resolve perpendicularly, up and down, we can work out what the normal reaction force is. And so, think about forces going up and down. Because it's in equilibrium, the up will balance with the down. And so the normal reaction force is the only force acting upwards. That'll be equal and opposite to the sum of the forces or components of forces acting downwards. And so that'll equal 0.3 g plus this 2.5 sine alpha, which we've calculated already, is 1.5, based on knowing that tan alpha was 3/4. So it's 0.3 g plus 1.5. So let's just calculate that now. So 0.3 g means 0.3 multiplied by 9.8, then plus 1.5. That gives us 111 over 25, 4.44. So that's 4.44 newtons. So then we can resolve horizontally. So the forces going to the left, in this case mu n, will equal the forces or components of forces acting to the right. So in this case, we'll have F max, which is mu multiplied by n, now we worked out what n is. N is 4.4 newtons. So mu times 4.4, which is mu n. So again, I can highlight that if you'd like. So this is F max, and that's F max as well, that's mu n. That's only force acting to the left, so that'll balance with the force acting to the right, which is just 2.5 cos alpha, which we worked out was just 2 newtons. So that's going to equal 2.5 cos alpha, which is just 2. So and therefore, mu will equal 2 divided by 4.44. So be prepared to round this to a suitable degree of accuracy, because this is going to be an awkward decimal. So 2 divided by 4.44, that's going to give us 0.450 newtons, or not newtons rather, just it's a coefficient, so it's going to be unitless, this one. So it's just 0.450 to either 3 significant figures you can think about, or 3 decimal places, either or. So that's our estimate for mu. And that's the last of worked examples. So now it's over to you folks to try some of these yourselves. So here's what I've suggested you try. So starting from page 130, try all of exercise 7a if you can stomach that. It will do you a lot of good in the Stats and Mechanics book in the Year 2 course. So try these, check your answers regularly using the back of the book. If you get stuck, ask someone you sat next to, or ask me in lessons. Don't use the fact you're not in lessons as an excuse. Email me, or even leave a comment in the comment section of this video. Thank you for watching. Please do subscribe. I'll see you all soon indeed. Bye again for now.